guys, so today we're gonna talk about an LED driver circuit, right? So in this episode, we just want to kind of talk about how we can turn on an LED using very simple passive components, just a resistor, and kind of go walking you guys through the steps of which you could design the circuit. Obviously, we're gonna do some back of a napkin calculations, and then we in the next episode we're gonna switch to some simulations, and then in the following up episode we're gonna talk about how to actually capture the schematic and then do the layout for a PCB, and then you could basically use it. So we can basically turn on an LED with a simple resistor circuit, right? So we can have a, let's call it a source like VCC over here. We could have a resistor and then we connect that to an LED and then that's a ground, right? So we have the LED here, we have the resistor here, and then if you just connect it to the plus volts, I mean, it could be anything from like 3 volts, 5 volts, or anything. You connect it to a resistor, and then following that series in that, you're going to connect it to an LED or any sort of a diode, right? So this is a simple circuit, right? You could easily turn on this LED, but the issue is as this VCC, as this voltage changes, right? As this voltage changes, so does the current through this resistor and then the current through this LED. And as we all know, LEDs obviously the more current kind of flows through it, the brighter it gets, right? So in a lot of applications, in real world applications, what we're trying to do is trying to design a circuit that drives LEDs at constant current, right? So now the question is, okay, how can we approach this? So what kind of a circuit can we design to make sure that there is a very specific amount of current that goes through this LED, regardless really of the input supply. I mean, we're gonna talk about the input voltage, what the range it could be. Obviously, like it can be like 0 volts, right? So it could be certain voltage over the driving of the turn on voltage of the LED, right? So assuming that that criteria is met, the voltage could basically change to any value. It doesn't matter because the current will always be the same. So how can we design it? So what kind of a circuit can do that? So let's just kind of have a simple drawing over here, right? So we have the VCC again connected over here, right? And then we have this LED, and this LED will connect. We're gonna connect it to a NPN transistor, right? We're gonna connect to an NPN transistor like that, and then we're gonna have a resistor over here, and then we connect it to a ground, right? So this NPN transistor, and as you guys might probably already know, NPN transistor, the way that they work is, so we have an NPN transistor, right? NPN transistor, um, and even PNP transistors, they are current controlled devices. So it means that we need to have some amount of current through the base, basically, of this transistor in order for this transistor to turn on, right? They're different than um, MOSFETs, right? So here, I just say, that for example, in a MOSFET, that we call them like NMOS, sort of, the equivalent of NPN transistors, but in a MOSFET um, package, they are voltage driven, right? So what's the difference? As I said, we need to make sure that if we're using an NPN transistor, you could use any sort of transistor. We're using NPN because NPNs are much simpler. They're actually cheaper, and they're, I mean, widely available, and you can use it in any sort of power rating and any sort of voltage rating. So they're pretty handy. So we're using NPN transistor in this case. NPN transistors, like I said, you need to have some current through the base. So how can we provide this current? The way that you can provide this current is very simple, right? So you can have another source, another sort of a power supply on this side. Let me just kind of get rid of this. All right, so yeah, you could have a source. You could have this source here. Let's just call it VS, right? That connects this, that basically, to this NPN, right? So here it will be some sort of voltage. But again, you don't want to, hook it up directly to a, power supply, right? So you want to have like, some sort of a current limiting resistor over here, right? So we're going to have some resistor in here that kind of limits the current. And we make sure that we have certain amount of current that flows through the base of this NPN, right? So this VS this could be obviously, any voltage really, because I mean the base of these transistors, like I said, they do have some ratings, but they're not really, because they're not a voltage driven device, they don't really care what that specific voltage is, as long as there's enough current that flows through the base. So here, I mean, most applications, in most like real world applications, we use basically an MCU, right? Like sort of a microcontroller. So we have an MCU here, which usually provides about, like, some MCUs are, 3.3 volts, some MCUs are 5 volts, right? So, doesn't really matter. We could assume either. So one application is using an MCU, right? You could have an MCU, and then this on voltage on this pin, right, would be 5 volts or 3.3 volts. And then you have, like, some resistance on here, let's call it R1, right? That limits the current through the base. Again, we can talk about it, but when we go through certain, like calculations, you can find out that the base current has to be within a certain amount, so that the basically collector emitter current kind of follows. There's that equation that kind of, follows that amplification because of the beta, right? The gain of NPNs. So I mean, NPN transistors, obviously they have a beta parameter, which is a gain, the current gain. It basically just means what's the current. So that it just explains that. Sorry about that. So it just says that the current through collector, which is the same as emitter basically, is beta times the current through base, right? So basically, because we have the option to control the current through the base, we can easily control the current through the collector, right? So that's pretty straightforward. So now that we figured this part out, now we can easily turn on this, basically turn on this node over here, and let's say we can pull it up to 5 volts, and then this NPN will turn on, right? So there's no issue with that. So we could actually pull it up, pull it high, and then it'll turn on. So this transistor will act basically as a short circuit, right? And then the current starts flowing, right? But now the thing is, well, we're not really controlling the current, right? Because I mean, even when the voltage increases, even the voltage changes, we still really won't be able to actually control the current through this LED, right? So how can we achieve that, right? So the way that we could do that is, we need to be able to sort of sample the current, right? So usually in most applications, we kind of sample current, obviously, uh, via a sort of a voltage sense, right? So we basically imagine we have this resistance, right? And then this resistor basically has certain current that goes through it, right? So it's a little bit hard. There are devices that we could sense current directly, obviously, 'cause they're current sense devices. But most of the ICs that you guys see out there, they actually sense the voltage across, sort of across this resistor in order to find the current through it, right? So it's pretty straightforward. It's just a simple Ohm's law, right? So I mean, the way that they do it is basically the sensing circuitry. What it does is it just says, well, I mean, I know that the current through this is just a simple Ohm's law, right? It's just, V over R. So I know what my R is, right? And whatever my voltage is, that voltage could be a simple sort of a reference voltage. Whatever that voltage is, I can easily find the current that goes through this resistor. So it's pretty straightforward, right? So if we just go back a couple steps, one quick second. All right. So now we're saying, okay, so now for this circuit, so how can we control the current, right? So here as you've seen it, I already put sort of a little resistor down here, which you could use it for any purpose. Honestly, you could just have it as a way to sort of limit current, right? Because if you think about it, when you pull this node, this VS node high, this uh you know NPN transistor will turn on, and then the current will flow from VCC all the way to ground, and you could basically, this resistor will be in series with LED, right? So you could basically just change that resistance value to adjust the current, total current through this, right? But the thing is, if the source changes, if the VCC changes, this will change as well. Like the current through that will also change, right? So that's what we don't want to have, right? We want to actually have an extra layer of um, sensing, an extra layer of control, right? So what we're gonna do in this case, which is pretty straightforward, is to take this circuit, right? Take this circuit and connect it to another, basically to the base of another NPN. Right. So yeah. So as you can see here again, we're gonna connect the basically, this sort of, this node of like the collector, I'm sorry, the emitter node of um, this transistor into the base of another NPN transistor, which basically connects the collector to the base of the first transistor, right? So, so what happens is, let's call this R2. I think I should probably just name these. Let me call this. Let me just clean up some of this mess I made. All right. So let's just call this Q1, right? We call this Q2, right? Just for simplicity. And yeah, so as you can see here, this transistor. So how does this transistor now work, right? So let's just go through the same steps. We said that when this transistor, when this Vs voltage right here, when this is high, right? This Q1 transistor will turn on. So the current will start flowing from VCC, goes through the LED, turns on the LED, it goes down, and then it goes through this R2 resistor, right? So um, this there will be some voltage, as I said, when we talked about resistors, right? When you have a current through a resistor, there will always be some drop across it, right? So depending on what resistor value we're using, we could basically control the current. How? Let me show you. So I mean, we have the current going through this R2 resistor. Um, and we know that most, basically 99% of NPN transistors, the way that they the way that they work is, so when they have some current going through the base, there needs to be a condition for which the NPN starts operating, right? And that is the um, base to emitter voltage. So the base to emitter voltage when the transistor is operating is usually about zero point 0.6, sometimes zero point 0.7 volts, 0.7 volts. So it obviously varies from different transistors, but let's say in this case it's zero point 0.6 volts, right? So what this saying is, when current starts flowing through R2, right, there will be some voltage across it, right? But we're saying that in order for us to be able to control that current through R2, which is similar, I mean, the current through R2, right, is basically same as current through um, the LED D1, let's call it. Let's call this guy D1. Right? Let's assume, because the VCC is changing, it goes higher, or something happens, we get basically more current that goes through R2. And as we discussed, obviously, V equals IR, right? Based on Ohm's law. So as we get more resistance, as we get more current through this resistor, we get higher drop, right? So when we get higher drop, what as we said, there will be more base current through the base of Q2 transistor, and then it'll be like subsequently there will be more current that gets sort of drawn out of base of Q1 through the collector of Q2. So now what happens is, you'll have less current at the base of Q1, right? And then that consecutively, again, as I mentioned, based on this equation, you get less current through IC, right? The collector of Q1. So that'll be less current through your LED. Again, this process happens like very quickly, and it happens in a closed loop fashion. So that's why, like, the overall, like, the actual current that goes through LED always stays within that specific, that specified um uh, uh current value through R2. So now the question is, okay, so how do we calculate that current, right? So we said that we have this VCC, right? And then we have this LED, and then we also do have this BJT over here, and then it connects to, another basically BJT like that. My apologies for my really bad drawing, but you get what I'm trying to do here. So then this is Q1, right? And this is like, let's call it D1 as we said, right? So what we said is, because the turn on um base emitter voltage of Q, transistor Q2 is zero point 0.6, right? We want to make sure that the current through R, which is the same as current through D, right? Like, D is basically D1 current is the same as IR current. We want that to be basically zero point 0.6 volts, right? Which is the reference voltage that we setting, right? At that base emitter voltage, like over here, right? Divided by the resistance value, right? So we're saying that for this application, we want this LED. We can look up the data sheet. We want this LED to only draw, let's say, 30 milliamps, right? So we're saying that at zero point 0.6 volts, reference voltage drop that across that R, the resistance value that we can find is zero point 0.6 divided by 30 milliamps, which is 20 ohms, right? So basically it's very straightforward now, right? So it's just saying that if we just have a circuit where we have one LED, and then we basically have a simple two NPN transistors, and maybe like two resistors. I mean, this resistor R1 over here, it's it's good to have. It's not necessary. Like I said, if you already directly connecting it to an MCU, to a microcontroller, microcontrollers usually don't don't supply that much current to their GPIO pins, so it wouldn't really matter anyway. But if you want to connect it directly, let's say you want to say that I want this circuit to be always on, right? So it's very simple, right? So basically all you need to do is, instead of having the node at the base of Q1 connected to the MCU, you're just having it directly connected to the VCC, right? So this could be just connected to VCC, but like this, and then this is just connected, say, directly to VCC, and then that's where, there you go. So now you have it connected directly to VCC. So this, it just means that this will always be on. So this circuit, as long as you select the right resistance value here, and you picked an LED that obviously turns on, for example, for 30 milliamp of forward current right through this LED, and also if your VCC is at least like point 2, point 3 volts over, like the VCC has to be point 0.2, 0.34 volts, probably over the forward voltage of this LED, right? So we need to make sure that that's true. Usually most LEDs, depending on for what application, but most of them, depending on the color, they start from like 1.9 volts all the way to like 3.2 volts. That's like most of the LEDs. And usually if VCC is 5 volts, that's already good enough. But we're gonna do like some power calculations later on. But for a back of a napkin calculation, that's all you need. You just need an LED, you just need two simple NPN transistors and a resistor. And then now you have a constant current LED driver, where it'll make sure that there will be a constant brightness no matter what the input voltage is, what the VCC is.